remembered to start recording. So we can switch to English. So it's a pleasure to introduce Dr. Manesco. Dr. Manesco got his bachelor's in engineering physics at USP São Paulo, Brazil in 2016. Then he got his PhD in materials engineering in 2021, also at USP São Paulo, Brazil. He spent during his PhD a year at Delft University of Technology working with Professor Akhmedov. And since 2021, he is at Delft University of Technology in Holland, in the Netherlands. And he's a postdoc with the Netherlands Organization for Scientific Research, working, I understand, with the group of Dr. Akhmedov. So today, Dr. Manesco is going to talk to us about quantum computation without qubits, universal control of local fermionic modes with Cooper pair splitters. So, Dr. Manesco, thank you very much for accepting our invitation, and the microphone is yours.
Thank you, George, for the kind introduction, and thank you for the invitation. It's great to be here and speaking with my Brazilian colleagues, and also trying to stimulate a bit the students to learn something maybe different, or maybe just bring something new for them. So yeah, today I'll be talking about quantum computation in perhaps a very different context to what you've been used to. So, well, maybe we're not used to quantum computation at all, so I'll spend some time talking about it. And this is mainly most of what I'll be talking today is the result of a work that I've done in collaboration with all these nice people here. We are all part of the Quantum Thinker group that is led by both Michael and Anton. So yeah, and special kudos here for Costas that did quite a lot of the heavy lifting here in this work. So yeah. To get started, well, also if you want to check our manuscript is on archive under review for quite a while now, but it's in there. And also if you want to try to run the calculations yourself in your computer, this is another DOI that I present here. You can actually find everything that all the codes that we use to perform all the simulations as we usually do here. So yeah. So just a disclaimer before I start, my background is not on quantum computation, even though we'll be talking quite a bit about quantum computation. So I hope that I don't disappoint people that make me questions about quantum computers, because I might not know how to answer those. I come from a very different background. I'm a condensed matter physicist, working particularly in mesoscopic phenomena. And yeah, this is a work where we realized that we could use some mesoscopic phenomena to come up with a new proposal for a quantum computer in a different way. So before I actually start talking about what we have done, let me just give a small introduction, because I know many of you are students here, and I think it's nice to go slowly with some concepts that you may not be familiar with. So we might start thinking, and this is actually something that I also learned very recently, how actually quantum computers are like. And well, we can start with thinking about classical computers, where we basically have those machines that take classical states, sorry, and we call those states qubits. So we create these machines that have states where, for example, you pass current or not pass current, and those define two classical states. And with those classical states, we can also add on top of them classical operations. So we can also, with those states, we can also perform operations. That's how our hardware actually do computations. And the quantum version of it is actually fairly similar. We also have we start with two quantum states, which we call qubits. And we realize that in these quantum states, we actually have a higher degree of freedom, because now we're not only constrained to zeros and ones. So we have a richer set of operations that we can actually perform with those set of states. And so we have the set of quantum operations that we can now perform on them. But the ideas are very much similar. It's mainly, this kind of quantum computer is mainly a quantum version of what we know as a classical computer. And this has many implementations nowadays. So there are many platforms where people actually have implemented quantum computers. For example, superconducting platforms with these superconducting qubits, where you have these Josephson junctions, and the excitations in there are your two-level systems. Ion traps, also similar idea. Spin qubits, also very similar. And something slightly newer here are the Andreev spin qubits, or just Andreev qubits as well, where you control Andreev levels to form your two-level system. By the way, I want to just tell everyone here that if you want to ask me questions, just feel free to interrupt me anytime. Actually, I'm not sure how the platform works, but I guess you can just raise your hand, and George, you can feel free to interrupt me anytime.
Yeah, we'll do that. No problem.
All right. So, okay. Now, say I just listed a few types of quantum computers, but why would we even care about spending time, effort, and money on building those? So, again, I'm not a quantum computer specialist, so the best thing I can do is Google. And actually, it's funny because when you Google it, you just find these very nice list of amazing applications, from AI, finance, cybersecurity, traffic optimization, manufacturing, drug discovery, batteries, material science, and the list goes on. I just stopped it because I got tired of copying. But actually, we're quite far from even get to those applications. I mean, most of the quantum computers are just too bad to even perform operations that will be needed to perform those tasks. The current quantum computers are actually nowadays being used to much simpler stuff. So, for example, real case uses look slightly more like these. So, realizing a topological order states on a quantum processor. This is an experiment from the Google collaboration, where they have their quantum computer and they use it to simulate a physical system. So this kind of gives a hint on types of problems that quantum computers are very much suitable to address. And it's kind of obvious, but quantum computers are good at solving quantum problems. So if you have a good enough quantum computer, of course, you need it to have nice gate fidelities and everything. But if you have a good quantum computer, this computer should be able to solve fairly well physical problems of quantum systems. So let's do an exercise here, and let's try to find one quantum problem that we could solve with a quantum computer. And a very simple case is a system where electrons interact. So let's look closely to this Hamiltonian. The idea here is that we just have a bunch of electrons in a lattice, and these electrons have some, for them to sit in a given atomic position, they pay some energy mu I. For them to hop from one position in this lattice to the other, they pay some energy t. And while they have these dynamics, they also have some repulsion energy that comes from this U here, which is essentially a Coulomb interaction in the lattice. So now, say I give you this problem Hamiltonian, and I ask you to find, for example, the ground state or excited states of this given Hamiltonian. So how do you even start to implement this Hamiltonian in a quantum computer? Well, there is a tricky part here because, again, our quantum computers are made of qubits. And if we want to simulate a system like these, where we have, for example, electrons interacting on a lattice, we're actually trying to simulate a fermionic system in a quantum computer, which means that we need to take qubits, which are these two-level systems, and where we describe all the dynamics via those Pauli matrices. We need to take these that has a very specific algebra. So we have these commutators and anti-commutator algebra here. And we need to map these into something that is actually fairly different, which are systems with fermions. And fermions obey another algebra, which is given by these relations here. So now we kind of need to find a way to take that fermionic Hamiltonian and map into a qubit Hamiltonian. And there are many recipes on how to do that. This is a fairly active research field trying to optimize this mapping and make it as efficient as possible. But the most naive way that someone would try, perhaps if you are somewhat familiar with the field, would be by using these Jordan-Wigner transformation, which you see here on the right. It takes these Pauli matrices, which describes our qubits, and on the left we have actual fermionic operators. So here the operator that creates a fermion in a given point in the lattice. Now we need to take then, well, you can already kind of see how complicated things are, because our Hamiltonian was just a bunch of those C's, which are these fermionic operators, and we now have to do all this complicated mapping and get a Hamiltonian in the other representation, a qubit representation. So just as a quick exercise, just to show how things look like, we just take this Hamiltonian, and basically all we need to do is find how to write down these products here of C dagger and C. And they look as this expression here on the right, where just basically just place the formula that I showed in the previous slide and substituted everything. I don't want to scare everyone here. You don't need to understand how these things work. I just really want to show how complicated things are going to look like in a bit. And if we do this substitution, what we very quick notice is that this Hamiltonian now looks, well, it was not great in the beginning, but now it looks actually awful. Particularly because of this term in the middle here that you see is highly non-local. And what do I mean by that? So if you look at this product here, this tensor product that I have in here, you see that this product is running over a bunch of indices, which means qubits in different places of your system, so many qubits. And you need actually many qubits to just describe a process of one electron going to another position, which before was a much simpler expression. By the way, can you guys see my mouse? I don't think so, right?
I don't think so.
Yeah, well, okay. I'll work without that, but if things get unclear, also please do ask me.
Okay.
So yeah, we got this very term in the middle here of the last.
Sorry,
yeah,
we can see it. We can see it. Yeah.
Yeah. Okay. Good.
Yeah, we can.
Great. So we got this nasty term here in the middle where we have a very non-local contribution to the Hamiltonian, and that makes mapping from going from fermions to qubits a very complicated process, and usually gives us a highly non-local Hamiltonian. So this is the first problem, but maybe you don't really care. Maybe, I mean, you're fine with doing some extra steps in your calculation. But you have to be aware that even if you don't mind non-local Hamiltonian, you also have a second problem, which is the extra overhead in your quantum computer. So every time you have a fermionic Hamiltonian, and you want somehow to solve this Hamiltonian, you need to go through this very first step where you map from one Hamiltonian to the other. And this causes an extra overhead, an extra time of calculation where you have just to wait to do something that's perhaps completely unnecessary. So then I raise a question here. Why don't we actually instead try to control directly fermionic degrees of freedom? So what do I mean by that? Instead of having qubits and having those two-level systems that are more like bosons, why don't we actually have, we take a system with a bunch of fermions and control the fermions directly to try to simulate the dynamics that we want in the first place? So this requires mainly two things. First of all, we need to know how to even perform computations with such a computer. So we need basically a recipe on how to perform universal computation with these computers. And the second thing that we need is a device. And just before I move on, I just want to also highlight something here. Maybe you were thinking, oh, now you're raising something that might be silly, because say I create this quantum computer where I actually have control of fermionic degrees of freedom. Does it mean that now if I just have a problem that I knew how to solve with my old qubits, do I have to map it back? And well, it is true, but it turns out that the mapping back is much simpler. So you barely have no extra overhead, and you don't have also these non-local Hamiltonians anymore. So this is great, because then if we actually manage to have these quantum computer, if we have a recipe and a device, they might actually be even in some sense, well, I won't say better, but they might they not only solve the problem that we started with, but they also work as great as another computer that just uses qubits instead. So let's start with the recipe here. And oh, sorry, what did I do? Okay, so let's start with the recipe here. So this the recipe is basically how we perform universal operations with a fermionic quantum computer. So say we already have it. How do we even do things with them? And it has been shown actually more than 20 years ago that you just need to coherently control these 4 operations. And those are actually all you need to perform universal computations with your fermionic quantum computer. So let's try to understand what they mean. So the first one is actually just exponent of the fermion number, which is actually just the Hamiltonian of a system where you just, so you take one electron and you change its energy, the energy of the state that this electron is sitting at. And the time evolution of the Hamiltonian that is doing that is actually implemented in the first gate operation. The second one is a hopping process. So you see that we annihilate an electron in one place of the lattice and create in another place, meaning that it's just the Hamiltonian that is supposed to perform a hopping from one side of the lattice to the other, or from one side of place in space to another. The third one is a bit trickier, because now you see that we're creating 2 electrons at the same time, or annihilating 2 electrons at the same time. We'll get to that in a minute. And the fourth one is have a product of more fermions that we had before. So we see here 4 fermionic operators, and they actually mean an interaction between fermions. So let's try to build step by step and maybe try to come up with a device that can actually perform all these operations. So if we have to think about a device, we need to first establish even how we want to encode those fermionic degrees of freedom, because we could think, for example, that the 2 fermionic degrees of freedom in our system would be like spin up or spin down. We will do something slightly different. So we just place 1 electron at a given point in space, and each point can have at most a single electron, cannot have an opposite spin or anything. It's just a single electron. And this is going to be how our quantum computer is going to work. So First of all, we need a way to confine electrons in space. And I come from a solid state and mesoscopic physics background. So every time you tell me that you want to confine a single electron, I'll immediately think about quantum dots. So what are those? So quantum dots are these basically these regions that are so tiny that their size actually compares with the wavelength of the electrons. And how do we do that? So to do that in a solid state system, you first of all need a system with very low electron density, which you can achieve, for example, in semiconductors. And second, you also need to be able to tune the electron density, because then we can do something fun with it. So look at this device on the right. I think it shows better what I'm trying to say. So look at this QDL here, the quantum dot to the left. You see there are three blue fingers coming here. One finger to each side and one finger in the middle. So these two fingers at each side, what they actually are supposed to do is just they lower the electron density almost to the level that you cannot really fit an electron in that region of space. So you really, how we call it, deplete completely this region, and we cannot put any electrons in here. So, and with this other region, you actually give a slightly higher electron density, such that you can just fill with a single electron. So, meaning that this region is about the size of the wavelength of your electrons. And if it's a material, it's the Fermi wavelength of this material. So now we just actually control these densities with voltages. So you see that all of those has a bunch of voltages connected here, which will, and all these voltages are going to control the electron density and make those quantum dots. So, all right, we managed to find a way to confine electrons in a given space, but this is not all, because even though this region is as small as the wavelength of the electrons, you can still fit, for example, two electrons at the same time with opposite spins. So to avoid that, what we're going to do is the following. We want our quantum dots to have single fermions. So first of all, we'll target a regime that at most we have one electron per dot. It can also have no electron at all, but at most it can only have a single electron. And to put an extra electron, it must cost so much energy that will never happen. So for that, to achieve this regime, what we need is a large charging energy. And what do I mean by that? We confine so much these quantum dots such that it has a very low capacitance. And as a consequence, putting one more electron costs a very high electrostatic energy. So you cannot really fill one more electron in this quantum dot because it will just cost too much energy. And the second point is that we want everything to have well-defined quantum numbers. And this is mostly for control of the system. We want to know very well how these electrons look like. So at this point, they can actually have any spin state. And to avoid that they have any spin state, what we do is we spin polarize those electrons by applying a Zeeman field. So the magnetic field that splits the two spin states. And then we apply such a large field that also populating the other spin state would cost way too much. So then we defined this regime and say you actually manage to fabricate quantum dots in such a regime. You also place a very large magnetic field, so everything is fulfilled to this point. Now, how can we actually continue from here? So say now we have two quantum dots. And I say two because this is the least amount of dots that we need to make something fun. If we have just a single electron, nothing, we cannot really do any of those operations that I just showed you. But if we have two, we can already implement all of them. So when you have those two spin polarized dots, it's actually fairly straightforward to perform one of the gate operations. because you just need to change the energy of the levels of each of those dots, and we do that by applying voltages. So we just change what we call on-site energy, and the time evolution of resulting from this change in the on-site energy already gives one of the gate operations that we want. The other thing that we need to do is that we can do if we have a system like this is remember that we depleted the region in between those dots to make sure that the electrons cannot escape. But we can now lower the barrier, the electrostatic barrier that is separating those dots. And with that, we allow tunneling from one dot to the other. And this tunneling is exactly the second gate operation that we had in that list of 4 gates that we need. So actually, to this point, we're already halfway through. Just with the 2 dots where we can control the tunneling between them, we already have 2 out of 4 operations. But then this is when things start getting a bit trickier because the other 2 are slightly more complicated to make. But before I move on, maybe I'll open the floor for some questions if there are any. I'll just give a few seconds in case anyone wants to ask something.
Hi, Antonio. Maybe we can ask your question already.
Yeah.
I'm gonna ask more detail at the end, but what about charge noise and coherence time? Are you gonna talk about this?
Yeah, I will. Great that you asked. Yeah, cool.
Okay.
Yeah, I'll get to that point later. I just won't say now because spoiler alert, we'll fix that. Okay. Well, I don't see any more questions, so I'll just continue. But if you want to interrupt again, just feel free to stop me anytime. All right, so now we have just 2 operations left. And the third one that we need to do is this one, where we are creating and annihilating pairs of electrons. Well, this is a bit trickier because now it's not just creating them, but they need to be created in a coherent way, such that it's kind of like one electron kind of knows that the other electron is also being created. And how can we possibly do that? Well, there is actually a solution for this problem, and all you need to do is take your 2 quantum dots and place a superconductor in the middle. Inside the superconductor, actually, the very superconducting phase transition is a process where we have electrons that were traveling almost without seeing each other, and below a certain temperature, they actually glue to each other, and we form these pairs of electrons, which are called Cooper pairs. So inside the superconductor, we have these pairs, but outside, there's nothing that would actually glue them together. So if we just place a superconductor in the middle of these dots, and one of the electrons wants to come out, because the other electron cannot just stay alone inside the superconductor, the other electron also comes out to the other dot. So this is a process that we call cross-Andreev reflection. I don't think the name is very important, really. All you need to know is that it is this process where 2 electrons come from the superconductor and leave to the 2 dots. And also the opposite process where we have 2 electrons, one at each quantum dot, and they come back to the superconductor. And also there is, of course, there is still the other process remaining. There is also the possibility of quasi-particles tunneling from the left to the right quantum dot, which is the second gate operation that I just showed you. So in principle, we are still we have all the 3 gate operations that we would need. The only tricky bit about this, everything that I'm telling you, that maybe so far looks very simple, is that we need to be able to control independently these 2 processes that you see here. These ECT, which stands for elastic cotunneling, that basically is just a tunneling event. So an electron tunnel from here to here. And this cross-Andreev reflection. We need to be able to control them independently. So can we actually do that? And this was actually done very recently for my colleagues here in Delft. So this is a figure from their experimental work, where they, well, this is one of the works. There are now a few more in different platforms, but you have these nanowires, and you see that there is a bunch of those fingers here that will define your quantum dot. So there is a quantum dot to the right here and another quantum dot to the left. And you see this region in the middle here has a combination of aluminum and platinum, which makes these a superconductor with a fairly large spin-arm coupling. So what this region is actually doing is making the nanowire right below, the region of the nanowire that's right below it, also a superconductor by a phenomenon that's called proximity effect. So now we have this island in the middle, which is a superconducting island. But now, because it's actually coating this semiconductor where it can control the electron density, by just applying this voltage here, this VPG, which is a plunger gate voltage, we can actually control how this superconductor kind of behaves. And by controlling how this proximatized superconductor behaves, we can actually selectively control this tunneling and this cross-band-derived reflection process. So here's just to show you how theory looks like. So these are just two spin configurations. So to the left, we have anti-parallel spins, and to the right, we have parallel spins. And you see that both work relatively similar. So what I show here on these orange lines is the cross-band-derived reflection probability. So the probability of electrons coming from the superconductor and leaving to one electron to each of those quantum dots. And the blue one is the elastic cotunneling, which is this process where electrons tunnel from one dot to the other. But you see now that these things are changing with some parameter here. And this parameter here is actually just that voltage right below the superconducting region. So you can actually go to regions where the blue line drops to 0, making you left with just the orange process, or the cross-band-derived reflection. And you can also go to finite values of these mu-m here, which is this voltage in the middle dot, and then you also have finite probability of tunneling from one dot to the other. So you can actually control that independently on the spin polarization. One configuration is slightly more sensitive to the other, to an external magnetic field, which is the transparency of these lines that you see here. But overall, they look the same, and you can, in principle, control them. Well, you see here it's not completely independently, because the orange line never really drops to 0, but they are independent in the sense that the matrices that implement these gate operations are linearly independent. They are not orthogonal, but they are linearly independent. So we can definitely work with that. And then, so these devices are known as Poor and Majorana devices, because they started in a very different context. Here in Delft, people were trying to create and measure those Majorana bound states in topological superconductors. And with those very tunable nanowires, they can actually achieve this topological regime. So with these devices, we actually have 3 out of 4 of the operations that we need for universal fermionic quantum computation. And there is only one more left, which is these that defines interactions between the electrons in the 2 quantum dots. But now things get a bit trickier, because we have the superconductor in the middle, which is gonna screen most of the electrostatic interaction between these dots. So what we actually need to do is just wire these dots to a capacitor connecting both of them, and the capacitive coupling between those dots will give an interaction that looks like that. So then we come up with this device here, which is the very basic building block for fermionic quantum computer. So we have, again, this middle dot here, the middle quantum dot that is proximatized by a superconductor. We have these 2 outer dots, where we can control their electron density by these voltages here, mu L and mu R. And we also have these tunnelings here, and this tunnelings is also something we can control with those finger voltages, finger gate voltages. And now we also have this extra capacitance here, and this capacitor has an arrow because it needs to be tunable. We need to be able to switch it on and off to perform the gate operations as we want. So, well, this is basically the device, and this is actually how we came up with this actually very early in the duration of this project. And most of the rest of this project was basically learning how to implement the gate operations and then optimizing this device. And that's what I'm going to talk about now. So first of all, can we actually even perform one of those gate operations? Let's look at the simplest one. This one is the cross-Andreev reflection. So that process where electrons come from the quantum dot and one electron go to each quantum dot. So we start everything with a wave function that is this psi 0, meaning that the wave function with no electrons. This 0 here is the occupation number in each one of those dots. And we apply a pulse. This pulse here is turning on and off this cross-Andreev reflection. And again, we can do that with the voltage in the middle dot. And we see that as time goes by, we actually couple this state with a state that has 2 electrons, 1 electron at each dot. And after some time, the probability of these 2 wave functions become the same. Now, there's something else here that you may notice, that we have actually many lines here. Some of those lines look very smooth, and some of them have some wiggly behavior. And this is happening because of something very simple. So you see that this blue line here is a very sharp step potential. Because it's very sharp, it actually stimulates transitions to other energy levels that we didn't really want to. This is a super fast process, so eventually it excites to states that we initially didn't want to. So this is what causes these wiggly lines here that you see in blue. But as we make these gates smooth and smooth, so if we apply it very slowly and ramp it up very slowly, all the voltages, we see that everything becomes smooth, and we have a behavior that we would actually try to target if we're building a quantum computer, because we want to avoid these transitions to other levels. So, all right, we can, and then, well, this is the simplest one. The other ones are slightly more complicated. So let me also give you the example of the most complicated one. And these, oh, sorry, oh, I went a bit way too much. Yeah, so this complicated one is the hopping process. So the tunneling from one quantum dot to the other. And the reason is very simple. So the process is this arrow here pointing to C dagger LCR. And if you look at the odd parity sector of this system, so the sector of your Hamiltonian that only contains states that are that in total form an odd number of fermions, we see that there are 2 processes that we can actually do here. One is this tunneling from one dot to the other, and the other one is just raising and lowering the energy, the relative energy between those quantum dots. But it turns out that every time you turn on this hopping, because we have that quantum dot in the middle that is proximatized by a superconductor, that's a bit of electron density that leaks out, and that renormalizes or changes the energy of these outer quantum dots. So the actual tunneling operation is not really orthogonal to this other operation, but rather something in between. And that then requires us to do some corrections here, because we want all the operations to be orthogonal to each other if we actually want to make sure that we control individually each one of those processes. So now we actually have to rotate it back to a way that everything becomes orthogonal again. And we can actually do that with Euler angles. But as you can see, it requires a product of many operations. So this big product here that goes all the way to n. And this n here depends on how bad is the angle between those two operations. So if this angle is 90 degrees between those two rotations, we actually just we don't need to do any of those corrections. So that would be the ideal case. But now, depending on how bad this, let me come back to it. Depending on how close this dashed line here is to the vertical one, we actually need to apply more and more operations to orthogonalize back this gate. Anyway, I don't want you to also focus too much on the equations. I just want to show you this is an annoying process and would be great to actually get rid of it. And the main problem why we cannot get rid of it is because we cannot just have a process where there is no renormalizations, and part of it is because we cannot turn off superconductivity in our device. But anyway, it works. It requires a few correction pulses, but it works. And now we come to the last part of it, which is actually look at the device and see if we find problems in it. So before I go to this very last part, are there any questions? And by the way, now I'm going to talk about charge noise. So your question is going to be answered very soon, Josh. Yeah, I don't see any questions. So I just jump then to this last part, which is how we started looking at the issues of this device. Because it does work, but to be a quantum computer, is it good? Is it any good, even as a proof of principle? Because I'm not saying that this is going to be the next generation of quantum computers, but is at least good enough for people to test in a lab if this device works as we expect. So we need then to identify problems. And the first problem that comes to mind is what Gerson pointed out, which is the sensitivity to charge noise. So let me explain that. If you have a bunch of quantum dots, I told you that we define those with those voltages that we just apply and generate electrostatic barriers. But it turns out that this voltage is not constant. There are tiny fluctuations to it. And these fluctuations are sufficient to actually decohere our quantum states. And in fact, the decoherence times are around the typical time where you can keep coherence is about 1 nanosecond. But now if we look at the minimal time for which we can apply those pulse operations, the lowest bound, the fastest we can actually perform those gate operations is about 50 picoseconds. Meaning that even with the best electronics that we have, because picoseconds is actually almost insane. I mean, I don't think I don't even think that the people here in Delft that are doing these devices can actually control to this level. Meaning that within 1 nanosecond, you can do like something around at most 10 gate operations. So this is not great. If we want to actually improve this device, we need to get rid of this sensitivity in some way. And the other problem I just told you, we cannot really turn off superconductivity, which makes some of the gate operations slightly more complicated, because now we have just a single parameter that controls those two events, the cross-Andreev reflection and the elastic cotunneling. And we also got these non-orthogonal gate operations. So it would be great to actually be able to turn off superconductivity, because that would make the gate operations much simpler. So at this point, we were thinking, and we had a very vague idea, which now a referee asked us to do something else on that, and because they identified that we could actually come up with a better device. And we started working on that and actually have a 2.0 version of the device that I just showed you. And maybe if you didn't pay attention enough, you will barely see the difference from the initial device to this second one. But what I have here is a larger superconductor, and you see now this superconductor is covering all the 3 quantum dots. And now we also have these tunneling probabilities here from the superconductor to these gates, which we could also control with an extra voltage. So this requires a slightly different setup. Nanowires are not going to work. But if we use a two-dimensional electron gas, which is just a two-dimensional system where you can you have very confined electrons, you can actually add those voltages and make a device layout that works just fine. And then you can actually turn on and off the superconductivity by just turning on and off these tunneling probabilities from the superconductor to these quantum dots. So first of all, we already get almost for free a device where we can turn on and off superconductivity. But that doesn't explain why I actually add superconductivity. I also connect the superconductor to these outer quantum dots. And the reason is actually very simple. So now the electrons that were in these quantum dots become what we call Andreev states. And Andreev states are excitations that happen inside the superconductor. And if we tune the parameters just right, what we can do is make these excitations become completely chargeless. So what I'm showing this plot is the charge of these states. And you see that if I just come to this delta mu, I won't enter in details of what this means, but it's just something you can control with those voltages. If you come exactly to the point where this delta mu is 0, you actually have exactly chargeless quasi-particles, meaning that now you are no longer sensitive to charge noise. Or in other ways to see that, you see that the charge operator is actually just the derivative of the Hamiltonian with respect to the chemical potential. And here is a point where the derivative is 0. So you are insensitive at least to second order to charge noise. And now you can look at all the other voltages in the system, and because all of them are very small, all of the remaining gate-dependent terms, so all the voltage-dependent terms that appear in your Hamiltonian are second order in these voltages. So we get some protection now against these fluctuations in charge because we are at the right, exactly at the minimum of energy dependence. So before it was linear, and now we are exactly at a minimum. And with that, I'd like to end my talk. So just trying to, first of all, giving an overview on how I imagine moving on from this point. So first of all, would be now we only have two fermions where we can control. The actual fermions are encoded in the outer dots. This middle one is just the auxiliary dots to mediate the process that we want. So extending this to a more complicated layout where we can have more fermions would be great. The other thing would be try to get rid of this middle capacitor. And maybe one way to do that, this is something that would require some experiments to actually show that. But you see that this superconductor is grounded, and meaning that the number of particles here is not really conserved. But now if you just make these completely disconnect this superconductor to the ground, then the particles cannot leave anymore this system. They are kind of enclosed in this system. And that creates some sort of capacitance that we can perhaps make use of. So maybe by connecting and disconnecting the superconductor to the ground, we can actually control the capacitance between these quantum dots. And finally, it would be great if someone actually fabricates and measures. I think this is perhaps fairly close because similar devices are here. So we just need to convince the right people to try it. And with that, I want to summarize my talk. So first of all, I hope I convinced you that we proposed a very basic building block for a fermionic quantum computer. It's cool because similar devices already exist, except for this extra capacitor, but maybe people can even get rid of them. If not, I think it's also a somewhat small modification in the existing devices. We also showed how to implement a universal set of gate operations in this device. And we've finally showed that if you add a tunable coupling to a superconducting reservoir, we can completely suppress charge noise and also simplify the gate operations. So with that, I end my talk, and I'll be glad to take any remaining questions. Thank you very much.
Dr. Manesco, thank you very much for the very nice talk, very didactic, and we are open to questions. Gerson?
Hi. Okay. Thank you, Antonio. Very nice talk. Okay. So George just passed the ball to me, but I was actually thinking about the question yet. But okay. So I have one that I'm not sure if it makes full sense, but I want to hear the answer anyway. So you have superconducting quantum computers, you have NEV centers and traditional gallium arsenide. With gallium arsenide quantum dots and NEV centers, you can also make a fermionic quantum computer, or am I wrong? What's the advantage?
So you don't have a universal set of operations because of these.
Yeah, what is missing there?
Yeah, so there you don't have this creation of coherent creation of pairs here. So these, let me go back. Yeah, this term here. This is what I don't think you could have in any quantum dots kind of system. So it can kind of do almost universal quantum computation, but you miss this one.
This one, okay. I'm also don't work with quantum computers, so I really, I wasn't sure about what was missing. And in the end, it caught us by surprise with the chargeless case with no charge noise. Can you go back to that? I want you. Can you explain like a clear picture of how you get the chargeless? You wrote it down mathematically, but like physically, what is the mechanism that gives the chargeless scenario?
Right. So let's say you confine, you have a quantum dot that is in proximity with a superconductor. So the electrons in there can do basically two things. They can hit a normal wall of this dot, or they can hit the superconductor. And when they hit the superconductor, they go through a process which is Andreev reflection. So they become a hole. So what, for those who are not familiar, let me try to explain. You have an electron coming to an interface, and then this electron cannot enter alone in the superconductor. So the only way for this electron to enter is if it binds with another electron from this metallic region, and these two electrons enter together, but it leaves out now a hole because you are injecting a single electron, and you are out with for conservation of charge, you have a single hole. So this process happens many times. So then this hole bounces in one of the walls of the nanowires and hits the superconductor again, and you have what we call an Andreev bound state. And these Andreev bound states are now, from a more quantum mechanical point of view, they are linear combinations of electron and hole states. And how much the contribution of these the electron hole weights is actually something that you can control by changing the chemical potential of the system. There are also other ways to do that. If you have a Josephson junction, so two superconductors, you can also connect them as a ring, and as you apply magnetic field, you can also go to something like that, as far as I remember. But or no, maybe not. No, forget what I just said. So, but with the chemical potential, you can go to this sweet spot where the Andreev bound states are chargeless, and this is all we gotta do to actually get to this neutral charge, neutral fermions idea. Just park exactly at the sweet spot.
We have
Thank you.
We have a question from Xavier. Xavier, please.
I just put in the type. I typed the question in the chat.
Okay. How big is the superconductor compound? The coherence length of the Cooper pair will not be a problem. Stabilize the Cooper pair.
Right. So this region in the middle must be. Let's see. For you to have one of those tunneling events, you need this quantum dot in the middle to be typically the size of the coherence length, and that's to ensure exactly that you can have these thinking from another perspective, this creation of two pairs of electrons is similar to inject an electron in one quantum dot and getting a hole at the other quantum dot. Why am I saying that? It's just because it's easier to think as something similar to a tunneling event. So for a tunneling to happen, you want the gap region in the middle to be not super large. Otherwise, you would not get any tunneling, meaning that your wave functions cannot decay from one side of the system to the other. And this decay length is the coherence length. So the middle quantum dot should be about the size of the coherence length for you to be able to perform these operations. Yeah.
Okay, thank you.
It can also be smaller. That's not an issue.
I have a pair of questions. This diagram that you showed in the beginning of the simpler system that was, I was very surprised that the level of control that they have in the Nature paper. I looked at that paper for the thesis defense. And right. This one, yeah. This one. Yeah. And the agreement with the theory, or better, the agreement of the theory with the experiment was really good. And they managed to see the soft spot and everything. So it's not too far, I believe, to be able to build the same in by your colleagues, right? Your colleagues.
Yeah, no, I think that's absolutely feasible. We just need to convince them. But,
to convince them that it's
worth also to make it universal in this extra capacitance. Okay. But in principle, yeah, I mean, the 3 out of 4 gate operations, they kind of already demonstrated. They just don't do time-dependent measurements, but it's essentially already done even. Because they do observe all those phenomena and they can coherently control all of them. So I think if there's something to be done here, it would be to actually try to do a time-dependent measurement where you try to keep track of some state that you prepare at the beginning and see how it changes with time. Okay. But yeah, I agree with you. The level of control is already fairly close to what you would need to perform those operations.
Okay, and the other question would be these dischargeless states you mentioned are Bogoliubov excitations?
Yeah,
exactly. Right. Okay. Yeah.
So yeah, you can. What happens here is like just to give a bit more details on what is going on. So you have those 4 levels. One of them is completely unoccupied. Then you have a 1 electron state with 1 spin, another electron with another spin, and then a 2 electron state. And what you're doing is you're actually coupling the 2 electron state with the 0 electron state in this cross-Andreev reflection process. So by coupling those, the average charge actually goes to 0 if you park at the correct place. Okay. And then the excitations have no charge. So the point here is that the quasi-particle excitations have no charge, not that the particles have no charge. Okay. So from going to this linear combination of 0 and 2 to the first excited state, which has just a single electron, since now the ground state is just the superposition of 0 and 2, which on average gives 1. Then going to the next to the extra level that has just a single electron, has no change in the average charge.
Okay. Okay. Yeah. So any more questions?
There's a raised hand.
Let me see. Well, there was one, but it was.
Yeah, but I see there is one in voting. Maybe the person posted in the wrong place.
It's yes.
Where is that?
Right.
Questions. How could quantum technology impact our daily lives in the future?
Well, that's hard to say. To me, since I'm working in here, it impacts quite immediately. But from a more practical point of view,
can I ask that question in a different way to help you answer? So what you're doing here, your whole motivation was the initial Hamiltonian there. So your quantum computer is a quantum simulator, right? I want to simulate Hamiltonians and study many-body physics on a quantum computer. That's a like Feynman point of view of quantum computation. So your quantum computer is a quantum simulator, or is a general purpose computer that can be used to, other kind of tasks? There are applications beyond quantum simulations?
Yeah, very good question. So let me try to start with this one about quantum technology. Honestly, it's hard to say. I mean, I think my friend Bruna is in the audience. She is the expert on quantum computation here. She might be able to actually reply this question properly, but I don't know. It's hard to say. I think quantum computers are fairly far from being for us to being able to use as like on a daily basis. Some people already use for doing research, as you just saw this paper that I showed from the Google collaboration. But I don't know. But it's hard to actually answer very in a very concrete way, perhaps. But about your question, Gerson. So yeah, the initial motivation is indeed to simulate fermions. But this is basically the same idea of any quantum computer, because let's think about now just one of those dots, right? So what we have here is also a two-level system. You can have an unoccupied dot and one occupied. Your dot can be completely unoccupied or occupied by a single electron. So this already forms the two-level system. And what we showed is actually the analogy to a two-qubit quantum computer. So we have two dots that are connected and coupled in a way that you can control in a universal way. Meaning that everything basically they can do with a qubit, you can also do with this quantum computer. So it's perhaps more suitable for doing quantum simulations than a qubit quantum computer, but it's not less suitable to do general computations than a qubit quantum computer. Well, except if you think about like how applicable it is, because I think it needs quite some time to get to the same point as most qubits in terms of quality, gate fidelity, but this is in terms of for just addressing your question, it's just as general. And then as I mentioned in the beginning of the talk, the mapping back from fermions to qubits is also very simple. So you can probably just do the inverse mapping very easily and apply everything you know for qubits to fermionic systems.
So maybe a last question: How far are we from simulating the Hubbard model with a quantum
there
computer?
are already some works out, even from here in Delft. I can remember that Leven's group, if I remember correctly, have one paper on simulating the Hubbard model with quantum dots. So they, of course, they don't have any superconductivity in there, so they cannot simulate an universal Hamiltonian, but they can already simulate Hubbard model. And I think there are already some results in quantum simulations of Hubbard model. Also, not only there, but I think also Google has a paper, I think, on simulating Ising model, which is also fairly close. Yeah, so there are things out there already on simulations of these simpler Hamiltonians, let's say. It's still fairly small system, so you cannot just simulate anything, but perhaps large enough as a proof of concept.
Okay. Yeah, because this, as you said, for people who work in the area, this would be huge. Because it's there is no solution to the Hubbard model, at least in 2 dimensions. So having a good simulation would be quite interesting.
Yeah, I think those, well, maybe I don't remember correctly now. I don't want to say the incorrect thing, but I think they have at least more than 2 sites in this works here in spin qubits. Yeah, So they use spin qubits as quantum simulators, and they managed to simulate Hilbert model with a few atoms.
Okay.
Yeah, for an infinite system, then I think we're pretty far. But and even for like something that resembles a material, I think we're still fairly far, but perhaps not as much. I don't know. Yeah.
Okay. Okay. So let me see here. No more questions. So if there are no more questions, let's thank the speaker again. Thank you very much for this nice talk. And I will ask you by email to send the slides if you please.
Yeah.
And so that we post together with the video in our YouTube channel. And I can send you, well, the YouTube channel is in our webpage. There is a YouTube sign there. So if you have any colleagues who want to check on the seminar,
Okay.
it will be posted there next week.
Absolutely. Great. Thank you very much for the invitation again. It was great to present.
Okay, thank you for accepting it.
Yeah.
So that's it for today. So thank you very much for everybody. We had a very good attendance today. So a good start to the semester.
Okay, thank you, Manesco. I have another meeting, so I have to go.
Yeah. No worries.
Thanks.
Yeah.
Okay. Bye
Keep
bye.
in touch. See you.
We stay in touch. Okay.
Yeah.